Once again, good morning, students. As a continuation for process states, we are going to look at processes from this point of view. And we've already discussed some of these. We said that a process contains what? A stack, a data section, a heap, and text. Yes, so the program code is what we call the text section. The stack contains temporary data, and data section contains global variables, and the heap contains memory that is dynamically allocated during runtime. We already know a program is a passive entity, while a process is an active entity. You know about the states of a process under the process lifecycle and ways process can be created running an application or created by the OS or spawned by an existing process. So a parent process creates children processes. This concept, I want you to carry it with you because we also have that parent and child thing with relations in database. Okay. Um, Parent process creates children process, which in turn creates other processes. And this it forms a tree of processes. Okay. So a process is identified by its process identification ID, the PID, and I showed you the PID in database when we opened our exam. Um, so resource sharing. This is how resources are shared. The parent and the children share all resources. The children share what? The subset of the parent's resources. And the parent and the child share no resources. So this is resource sharing options. So it could be that the parent and the children share all the resources. It could be that the children inherit a subset of the resources that the parent is enjoying, or the parent and the child will not share resources at all. And look at the execution options. The parent and the children execute concurrently at the same time, or the parent waits until the children terminate before it executes. So here's the tree of processes in Linux, and basically init, initialize. So you have what? Login, kthread, sshd. But these are all processes. And you see, the parent process is at the top, and it has children that are login, kthread, sshd. And login has a child process also that is bash. And bash also has two children processes. Yes. So this is a typical example, a tree of processes in Linux. Address space. So a child duplicate of parents. Child has a program loaded into it. So in Unix example, using Unix, we use the function or the keyword fork, and that creates a new process. And we use execute, exec, system call use after a fork to replace the process's memory space with a new program. So you look at fork, then what? A child, then execute and exit. Or fork a parent, then wait, then resumes. So this is C code on forking separation. Don't get confused with this. These slides are from my postgraduate, so it contains some information that is pretty much above your level and standard. So now process termination, and it's given us 7 ways that a process can be terminated. Either it's completed, or there's a timeout, or the OS has to intervene because maybe there is a deadlock, or the parent dies, or the parent is killed. That is the parent process. So once the parent process is terminated or killed, yes, the child process can also follow along, or the parent process can kill the child process, or maybe when there's an error condition or there is not enough memory available. So processes execute last statement, then ask the OS to delete it using exit system call. Processes resources are deallocated by the operating system. Yes. You see, I told you the OS is responsible for allocation and deallocation of resources. So if the process is terminated, yes, the resources, the OS deallocates the resources. Many web browsers run as single processes. So browser process manages the user interface, disk, and network input and output. Processes render process renders the web page and deals with the HTML. So it runs in sandbox, restricting disk and network I/O, minimizing effects of security exploits, minimizing the chance for you to try to exploit or explore further for security purposes, and plugin process for each type of plugin that is used. This is the process control block, which we visited in our first lecture. Process identification, which we know it uniquely identifies the process, is a numeric identifier that is allocated to a process once the process is what? Created, that is new. Okay. User visible register. A user visible register is one that may be referenced by means of the machine language that the processor executes while it is in user mode. So typically there are about 8 to 32 of these registers, although some risk implementation have over 100. So we know about the architectures, we know about the risks, we know about the CISC. Yes. So we have control status registers too. We have program counter, condition codes, status information, and we also have the stack pointer. So you see where the stack pointer is again, the SP. Each process has one or more LIFO system stacks associated with it. Stack is used to store parameters and calling addresses for procedure and system calls. So note that down. What the stack is used for. It is used to store parameters. And when I say parameters, you can, in a function has values or parameters. So it is used to store parameters and calling addresses for procedure calls and system calls. The stack always the stack pointer always points to what? to the top of the stack, always. All right, scheduling and state information. So we say a process state defines the readiness of the process to be scheduled for execution. It could either be ready, waiting, running, halted, or so. Priority. One or more field may be used to describe the scheduling priority of the process. In some systems, several values are required. Event. Identity of event the process is awaiting before it can be resumed. So if it is waiting for a certain process, so it's in a waiting state, the event is also allocated a number. So the OS knows what kind of event it is waiting for. Data structuring. A process may be linked to other process in a queue, ring, or some other structures. So all processes in the waiting state for a particular priority level may be linked in a queue. Interprocess communication. That is how processes communicate with each other. So various flags, signals, and messages may be associated with the communication between two independent processes. Some or all of this information may be maintained in the PCB, which is the process control block. So in memory management, the section may include pointers to segments or page or tables that describe the virtual memory assigned to this process. So now we see virtual memory here again. Now let's look at context switch. Being able to switch from one process to another. That is, you save the state of the process, then you switch to another one, then you switch to the other one, but always, it saves the state of the process. So when CPU switches to another process, the system must save the state of the old process and load the saved state for the new process through context switch. So context of a process is represented in the PCB, process control block. And context switch time is overhead time. Yeah, it's extra time, overhead time. The system does no useful work while switching amongst processes. So the more complex the OS and the PCB, the longer the context switch takes. So some hardware provides multiple sets of registers per CPU and multiple contexts loaded at once. So this is a diagram of how it switches from one process to the other. So you have process P naught on your left and you have process P1 on your right. So you'll notice that from P naught, there is an interrupt or a system call. So it saves its state because the arrows are showing the execution as it's trying to execute. So it saves the state onto the PCB of P naught. Okay. Then it reloads the state of P1. So there's been a context switch here. So P1 is loaded and P1 will continue executed. Then um, what ends up happening is that there's an interrupt or a system call. So we save the state of process one. And as we save the state of process one, we reload the state of process zero or P naught, and it continues its execution. Process scheduler. The process scheduler selects among available processes for what? The next execution on CPU. So we have the process schedule. Yes. And under the process scheduler, we have the long term. Okay, we have the long term scheduler, the short term scheduler, and the medium term scheduler. And we'll look at each one of them. So, process scheduling maintains scheduling queues. We already know what the job queue is, the ready queue, we have the device queue. This is the flow of the queues in this diagram. So the short-term scheduler, it selects which process should be executed next, and it allocates the CPU to that process to execute. So the short-term scheduler is invoked frequently. Yes. Then we have the long-term scheduler. And the long-term scheduler, it selects the process should be brought into the ready queue. So we already know what the ready queue is. The ready queue is there for processes that want to get access to the processor to for CPU time. So we said that the short-term scheduler takes this process and it does what? It gives it the CPU for it to execute. Okay. Now, the long-term scheduler selects the process and places it into the ready queue. So the long-term scheduler is invoked infrequently, yes. And the long-term scheduler controls the degree of what multi-programming. Now, processes can be described as either input and output bound process or CPU bound process. So input and output bound process spends more time doing input and output than computations. Many short CPU bursts. That is when we say a CPU burst is, let's say we can have a process, right? And the process might have to execute in maybe 3 cycles because it will execute for a period of time. Then maybe there's IO, so it will halt or it will be put into a waiting state. Then it'll come back, then execute. That's the second burst. It'll halt, come back. That's the third burst. Okay. So CPU bound process spends more time doing computations, few very long CPU bursts. So the long-term scheduler strives for good process mix. Now let's look at the medium-term scheduler. The medium, so we said we have what the short-term scheduler, which is responsible for picking the process and assigning the CPU to the process. Um, the long-term scheduler is responsible for placing the process in the ready queue. And we have the medium-term scheduler, and it can add a degree of multi-programming, can be added if degree of multi-programming needs to decrease. So it removes processes from memory store on disk, bring back in from disk to continue executing. So it does what we call swapping. That's for the medium-term schedule. IPC. So processes with a system may be independent or cooperating. We have independent processes and we have cooperating process. So cooperating processes can affect or be affected by other processes, include sharing data. So reason for cooperating process is information sharing, computation speed, modularity, and convenience. And cooperative processes need the IPC. And there are two models of the inter-process communication, which is message passing and shared memory. When we say shared memory, it means that there is a region that is created whereby the processes can communicate through that region and they can be able to even share data or share files. Then you have the message passing, that is the processes passing messages to one another. So, message passing, process A, process B, and that's the message queue. So, the messages, if you look at the arrow, process A is passing a message, MOM1, blah, blah, blah. Then process B can also pass messages, and they are able to communicate through this message passing. Then you have the shared memory, and what is happening here is that a region is created, and this region is a shared memory between process A and process B. So independent processes cannot affect or be affected by the execution of another process, but cooperating process can affect or be affected by the execution of another process. So advantages of process cooperation is information sharing, computational speed, modularity, and convenience. Unbounded buffer, producer consumer problem. Unbounded buffer places no practical limit on the size of a buffer. And bounded buffer assumes there is a fixed buffer or size. And when we say buffer, we know what a buffer is. A buffer is maybe a reserve area or a reserve region or a reserve memory that is being used. When so this is shared data. This is a code in C programming. Don't worry much about this. So an area of memory shared among the processes that wish to communicate. The communication is under the control of the user's processes, not the OS. And major issues is to provide mechanisms that will allow the user processes to synchronize their actions when they access shared memory. So we've looked at synchronization and we'll look at it again. Yes, process synchronization. So in interprocess communication, you have the message system. Processes communicate with each other without resorting to shared variables. IPC is send and receive. That is the interprocess communication. And the message size is either fixed or variable. So if process P and Q wish to communicate, they need to establish a communication link. Then they exchange messages. Then is the acknowledgement of send and receive. How are links established? These are some of the questions we can be asking. So the links can be implemented physically or logically. The physical links, there's shared memory, or there's a hardware bus system that allows the message passing to happen, or it can be networked. Then logical, it could be direct or indirect, or we can employ synchronous or asynchronous, and automatic or explicit buffering. So direct communication, you have process P. So send, you said P, then the message. So sends the message to P. So it means that in the parameter you have the destination, then you have the message. So the process Q, it's receive process Q and the message. So it receives a message from process Q. So P will receive a message from process Q, just in the same format. Okay. So if process Q sends the message, It's it indicates that I'm sending the message to P and the message follows. Then when Q um, when P receives it, it knows that the message is coming from Q and the message, it reads the message. Okay. So properties of communication link. Links are established what automatically. A link is associated with exactly one pair of communicating processes. So when we say one pair, that is two. Okay, a pair, two. So between each pair, there exists exactly one link. And the link could be unidirectional or it could be bidirectional. So messages can also use mailbox. Messages are directed and received from mailboxes, also referred to as what? Ports. Yes, I prefer using the word ports. So each port has a unique ID. Yes, yes, I told you. HTTP uses port 80. HTTPS uses port 443. MySQL uses port 3306. So on and so forth. So it creates a port, send and receive messages through this port, and destroy the port. Okay, let's look at this synchronization. So message passing can be either blocking or non-blocking. Blocking is considered synchronous. Blocking send. The sender is blocked until the message is received. Blocking receive. The receiver is blocked until a message is available. Non-blocking is considered asynchronous. Non-blocking send. The sender sends the message and continues. Non-blocking receive. The receiver receives a valid message or null message. So different combinations are possible. If both send and receive are blocking, then we have a rendezvous. These are C codes. So queue of messages attached to the link implemented in one of three ways. Can be implemented by zero capacity, that is no messages are queued in a link, or bounded capacity, a fixed length of messages, sender must wait if link full, or unbounded capacity means an infinite length and sender never waits. So this is an example of IPC system POSIX. Don't worry about these parts, these slides. This is C codes. All right. I think yeah, let's look at sockets. Let's look at the most important. Okay, let's continue from here. Message passing through advanced local procedure call uses these ports, and communication works as the client opens and handle on the subsystem connection port object. So the client sends a connection request. The server creates two private communication ports and returns the handle to one of them to the client. The client and server use the corresponding port handle to send messages to or callbacks and listen for replies, so to communicate with each other. So you have the client and the server. The client on the left, the server is on the right. So client sends a connection request through the connection port and it is sent to the server. And the client communication port is communicating by sending messages to the server communication port, as the server communication port is also sending messages to the client communication port for the client and for the server. Okay, and this is the shared section object, which is a bidirectional communication between the client and the server. So communication and client server system. So when we say client server, um, it's when you connect your computer to access resources from a different computer or a different system. Yes. So if you look at SIMT, SIMT has a server, and mm, you have users that connect to the system either to check your results or check your school fees or your payments. Yes, so you are the client, and the server is providing that information or that request for you. All right. So sockets, remote procedure called pipes, or RMI. What is a socket? A socket is defined as an endpoint for communication. Yes. So we concatenate, we put an IP address and a port number at the start of the message packet. So the socket, so you see the socket will have an IP address. It can have an IP address of 161.25.19.8, and it has a port number of 1625. So if you sometimes look at when you go to your browsers, you go 127.0.0.1, and you can put colon, I think 8,000, colon 8,000 is, I think, Django. You have colon 3,000, I think that is for Laravel. So it is the port it is using. All right, so when you see the colon after the IP address, it is talking about the port. Then all ports below 1024, 1024 are well known, used for standard services. So special IP address 127.0.0.1, which is also referred to as loopback. You'll be looking at it in um, data communication. Yes, yes, to refer to the system on which the process is running. So this is how the socket is created. So you have the web server and you have the host. So the host wants to communicate onto the server. So the socket is created, and the host has an IP address of 146.86.5.20, and it has opened a port 1625.1625. Then the web server has an IP address of 161.20.25.19.8, and it is using what, port 80, which is what, HTTP. Okay. So there are types of sockets. We have connection oriented, that is TCP, and we have connectionless, that is UDP. Now, with TCP, when a message is sent using TCP or communication is being done, there is the acknowledgement. But with UDP, there is nothing like an acknowledgement. So the only shortcomings of the UDP is that when your messages are sent, you won't know that it is sent. Then you have the RPC, remote procedure call, and it abstracts procedure calls between processes on networked system. I think we are going to keep our session here. Yes. And we will continue with scheduling. Yes. Thank you.